Hello students, let us see some examples. First example is if f is defined on closed interval 0 1, show that f of x is equals to 1, x is not equals to 1 by 2, 0, x is equals to 1 by 2, x is equals to 1 by 2, then show that f does not belong to Riemann integrable on closed interval AB. Means what? F is not Riemann integrable on closed interval AB. Okay. Let us see solution by dividing. Sorry, here is closed interval 0. Closed interval 0 1 into n equal parts. Let sigma n be the subdivision of closed interval 0 1 and we have sigma n as sigma n is equals to, it is subdivision of closed interval 0 0 1 by n, 2 by n, 3 by n and so on up to n by n is equals to 1. Okay. Let I1, I2 and so on up to In be the subdivision be the component interval of closed interval AB. Component interval of closed interval 0 1. Okay. And length of I1 is equals to length of I2 is equals to, and so on up to length of In is equals to 1 by n. See here, I1 is 0, interval 0 1 by n. Length of I1 is 1 upon n. Similarly, length of I2 is 1 upon n and so on up to length of In is equals to 1 by n, as I1 is equals to closed interval 0 1 by n, I2 is equals to closed interval 1 by n, 2 by n and so on up to In is equals to closed interval n minus 1 upon n, n by n. Okay. Now here we have to show that f is not Riemann integrable on closed interval 0 1. For that we will show that f is upper integral is not equals to lower integral. To calculate the upper integral we have to calculate UF sigma, and to calculate the lower integral we have to calculate lower sum. Okay. So we know the formulas of UF sigma n and LF sigma n. For UF sigma n we have to calculate MFIK, and LF sigma n we have to calculate small mfik. Okay, so small mfik, mfi1 is equals to least upper bound of f of x is belongs to I1, which is equals to mfi1. Here students, see here, least upper bound for this f is, for this interval is 1 by n, but our function is only takes two values, 1 and 0. So obviously its upper bound, least upper bound is 1 and greatest lower bound is 0. So least upper bound of f of x is 1. This is for MFI. Similarly, MFI2 is also least upper bound of f of x such that x belongs to I2. This is also 1, and so on up to capital M F I N is also 1. Similarly, we calculate small m f I1, which is equals to greatest lower bound of f of x. Here greatest lower bound for function is only 0. So here this is 0. Small mf I2 is also 0, and so on up to small mf In is also 0. Okay. Now write down the formula of UF sigma n. That formula is summation k runs from 1 to n capital M F I K into mod I K is the formula. Okay. Now put all the values. If you put k is equals to 1, so it becomes capital MFI1 into mod I1. MFI1 is, which is equals to 1 into mod I1 is 1 by n, plus 1 into 1 by n, plus and so on up to plus 1 into 1 by n is 1 by n. Okay, this is nothing but 1 by n plus 1 by n plus and so on up to plus 1 by n. This is n times, so this becomes n into 1 by n, which is nothing but 1. So we will get UF sigma n is equals to 1. Now calculate LH sigma n is equals to, obviously this is 0, but we will calculate it here. Summation k runs from 1 to n small m f I k into mod I k. Okay. Small m, if you put k is equals to 1, mfi1 is 0 into mod I k 1 by n plus 0 into 1 by n plus and so on up to 0 into 1 by n. This is equals to 0. Okay. Now upper integration from 0 to 1 bar f is equals to greatest lower bound, or here I will write GLB of UF sigma. Here UF sigma is 1, so its greatest lower bound is 1. Lower integral f is equals to least upper bound LF sigma. Least of LF sigma is 0, so this lower integral is equals to 0. Therefore we will get upper integral is not equals to lower integral f. Therefore f is not Riemann integrable on closed interval AB. Therefore f is not Riemann integrable on closed interval AB. Okay. Now let us see next example. Next example is prove that pi cube upon 18 is less than or equal to integration from 0 to pi x square dx upon 5 plus cos x is less than or equal to pi square upon 12. Okay. We have to prove that this. Now see solution, how to solve this type of problems. Okay. See here integration from 0 to pi means your x lies between closed interval 0 pi. Since x belongs to closed interval 0 pi. Okay. Therefore, cos x is lies between -1 and 1, because cos 0 is 1 and cos pi is -1. That's why -1 is less than or equal to cos x is less than or equal to 1. Okay. Here denominator is 5 plus cos x. So we will add here throughout 5. Our aim is to obtain this function x square upon 5 plus cos x. Therefore, here adding throughout the 5, we get 5 minus 1 is 4, which is less than or equal to 5 plus cos x, which is less than or equal to 6. Taking reciprocal thoroughly, what we will get? 1 upon 4 is greater than or equal to 1 upon 5 plus cos x, which is greater than or equal to 1 upon 6. Here we require x square upon this function. So we will multiplying by 6. What we will get? Sorry, x square. So here we will get x square upon 4 is greater than or equal to x square upon 5 plus cos x, which is greater than or equal to x square upon 6. Okay. Integrating all the sides between the limits, all the sides between the limits 0 to pi or 0 to with respect to x. Okay. Therefore integration from 0 to pi x square upon 4 is greater than or equal to integration from 0 to pi x square upon 5 plus cos x, which is greater than or equal to integration from 0 to pi x square upon 6. Sorry, here is dx into dx. Therefore, integration of this is here 1 by 4 is constant, and integration of x square is x cube upon 3. 3 into 4 is 12. Limits from 0 to pi, which is greater than or equal to integration from 0 to pi x square upon 5 plus cos x dx, keep as it is, which is greater than or equal to integration of this is x cube upon 18 from 0 to pi. Okay. This will be x cube, means this is pi cube upon 12, which is greater than or equal to integration from 0 to pi x square upon 5 plus cos x dx, which is greater than or equal to pi cube upon 18. That is, pi cube upon 18 is less than or equal to integration from 0 to pi x square upon 5 plus cos x dx, which is less than or equal to pi cube upon 12. Okay, friends, we have proved which we want to prove. Okay. Now let us take one example for homework. Second example, prove that 2 pi square upon 9 is less than or equal to integration from pi by 6 to pi by 2 into x dx upon sin x, okay, which is less than or equal to 4 pi square upon 60. Okay, This is similar of example number 1. Okay. Let us take third example. Third example is prove that integration from 0 to pi by 2 x upon 3 sin x plus 4 cos x into dx is greater than or equal to pi square upon 40. Okay. See here solution. Here your x is lies between 0 and pi by 2. So in closed interval 0 pi by 2, sin x is increasing function. Increasing function. Is it correct? Yes. Because sin 0 is 0 and sin pi by 2 is 1. Since why this is? Because sin 0 is equals to 0 and sin pi by 2 is equals to 1. Okay. This is the reason. Sin 0 is less than or equal to sin x is less than or equal to sin pi by 2 obviously. Therefore 0 is less than or equal to sin x is less than or equal to 1. Here we require 3 into sin x. So we will multiply throughout 3. So we will get 0 is less than or equal to 3 sin x is less than or equal to 3. Suppose call this equation number 1. Also in closed interval 0 pi by 2 cos x is decreasing function. Cos x is decreasing function. Why? Because cos 0 is 1 and cos pi by 2 is 0. So we will get cos 0 is greater than or equal to cos x is greater than or equal to cos pi by 2. So this is 1 is greater than or equal to cos x is greater than or equal to 0. This is 0 is less than or equal to cos x is less than or equal to 1. Okay. Here we require 4 into cos x. So we will multiply throughout 4. 4 cos x which is less than or equal to, call this equation number 2. So adding equation 1 and 2 and equation 1 and 2, what we will get? We will get 0 is less than or equal to 3 sin x plus 4 cos x which is less than or equal to 4 plus 3 is 7. Okay, that is this we can write as 3 sin x plus 4 cos x is less than or equal to 7. Okay, taking reciprocal on both sides we will get 1 upon 3 sin x plus 4 cos x is greater than or equal to 1 by 7. Okay. So here taking integration or here no need to, okay, taking integration from 0 to pi by 2, here we will get 1 upon 3 sin x plus 4 cos x into dx is greater than or equal to integration from 0 to pi by 2 1 by 7 dx. Okay, this will be keep as it is 3 sin x plus 4 cos x into dx which is greater than or equal to here 1 by 7 from, sorry, derivative of 1 by 7 is, this is x by, okay, sorry, here we requires x, so here we will multiply x. This is x by 7. So this is x square upon 4t. This is x square upon 4t. Okay. This limits from 0 to pi by 2. So we will get integration from 0 to pi by 2, 1 upon 3 sin x plus 4 cos x dx, which is greater than or equal to, here take this 1 by 14 common, x square is, put upper limit and lower limit, pi square, x is pi by 2, but it is whole bracket square. Therefore integration from 0 to pi by 2 upon 3 sin x plus 4 cos x into dx, which is greater than or equal to 1 by 14 into pi square upon 4. This is nothing but integration from 0 to pi by 2, 1 upon 3 sin x plus 4 cos x into dx, which is greater than or equal to pi square upon 56. Sorry, here is pi square upon 56. Okay. Hence we have proved which we want to prove. Okay. I hope all of you understand this type of examples. Okay. Let us see next topic, fundamental theorems of calculus. In this first concept is primitive. Primitive means integral. Let f be bounded real valued function. Let f be bounded real valued function defined on closed and bounded interval AB if there exists a function phi of x defined on closed interval AB such that phi dash of x is equals to f of x for all x's belongs to closed interval AB, then phi of x is called primitive or antiderivative of f on closed interval AB. Okay. For example, primitive or integral of sin x is minus cos x. Okay. Primitive means what? It is integral of a function. Okay. Next definition, integral function of integrable function. Okay. Let f be bounded function on closed interval AB closed interval AB, which is integrable on closed interval AB, then phi of x is equals to integration from a to x f of x dx is less than or equal to x is less than or equal to b. It's called integral function of f. First fundamental theorem of calculus. Theorem statement is, if f is continuous on closed and bounded interval AB, okay, and if capital F of x is equals to integration from a to x f of t, this f is capital and this f is small, dt, a is less than or equal to x is less than or equal to b, then f dash of x, capital F dash of x is equals to f of x. If f is continuous on closed and bounded interval AB, and if capital F of x is equals to integration from a to x f of t dt, then f dash of x is equals to f of x. This is the first fundamental theorem of calculus. Okay. Here we will not discuss the proof of this theorem because proof is very lengthy. Now next see one theorem. If f is Riemann integrable on closed interval AB, if f of x is equals to integration from a to x f of t dt, a is less than or equal to x is less than or equal to b, and if f is continuous at x0, then f dash of x0 is equals to f of x0, where x0 is belongs to closed interval AB, Here what is statement? If f is Riemann integrable on closed interval AB, if f of x is equals to integration from a to x f of t dt, and if f is continuous at x0, then f dash of x0 is equals to f of x0, where x0 is belongs to closed interval AB. Okay. Here we also not discuss proof of this theorem. Okay. Let us see next theorem. If f dash of x is equals to 0 for all x's belongs to closed interval AB, then f is constant on closed interval AB, that is f of x is equals to c for all x belongs to closed interval AB. We know that if derivative of a function is 0, then that function is constant. But here we have to prove this. Okay. Let actually here we can't say let because it is already we have given since, or let's say we have f dash of x is equals to 0. This is for all x belongs to closed interval AB. Okay. Since f has derivative, see here f dash of x is equals to 0 for all x belongs to closed interval AB. Means f has a derivative at every point of, means f has a derivative at every point of closed interval AB, then f is continuous on closed interval AB. Why this is? Because every differentiable function is continuous. Okay, every differential function is always continuous. Okay, therefore there exists, f is continuous on closed interval AB. Okay, so for here a is less than or equal to x is less than or equal to b, means what? Closed interval ax is a subset of closed interval AB. If f is continuous on closed interval AB, then f must be continuous on closed interval ax. For f is continuous on closed interval ax and is differentiable on closed interval x, because here f has derivative at closed interval ax. That's why there exists a point c belongs to open interval ax such that f dash of c is equals to f of x minus f of a upon x minus a. Okay, but here we have what we have given. This is by law of mean, but here f dash of x is equals to 0 for all x belongs to closed interval AB. Means this c is belongs to this closed interval AB. Therefore f dash of c is equals to 0. Since c is belongs to open interval x, which is a subset of closed interval AB. Okay. Therefore we will get f of x minus f of a upon x minus a is equals to 0. That implies f of x minus f of a is equals to 0. Therefore we will get f of x is equals to f of a for all x belongs to closed interval AB. Okay, this f of a is nothing but constant value, so we will get f of x is equals to c for, but this is for some c belongs to closed interval AB. Therefore f is constant. F is constant on closed interval AB. So always remember that if derivative of a function is 0, it means that function is constant. Okay. Let us take one more theorem. If f dash of x is equals to g dash of x for all x's belongs to closed interval AB, then f minus g constant, then f minus g is constant on closed interval AB. That is what? F of x is equals to g of x plus c for some c belongs to R. Students, proof of this theorem is similar to proof of previous theorem. Okay, just here replace f by f minus g. You will get the proof of this theorem. Okay, now let us see second fundamental theorem of calculus. Second fundamental theorem of calculus. We'll see second fundamental theorem of calculus. Okay, if f is continuous function on closed and bounded interval AB, and if phi dash of x is equals to f of x, a is less than or equal to x is less than or equal to b, then integration from a to b f of x dx is equals to phi of b minus phi of a. Solution. See here, what is second fundamental theorem of calculus? If f is continuous function on closed and bounded interval AB, if phi dash of x is equals to f of x, which is here x belongs to closed interval AB, then we have to show that integration from a to b f of x dx is equals to phi of b minus phi of a. Now we will see proof of this theorem. Proof is here, let capital F of x is equals to integration from a to x f of t dt. This f is capital and this f is small. Okay, a is less than or equal to x is less than or equal to b. Therefore, f dash of x is equals to f of x. A is less than or equal to x is less than or equal to b. Here, let capital F of x is equals to integration from a to x f of t dt. Here, see here, we have given, since f is continuous function on closed interval AB, therefore capital F dash of x is equal to small f of x by first mean value theorem. Okay, here in hypothesis we have given what phi dash of x is equals to f of x. A is less than or equal to x is less than or equal to b. Therefore, see here, RHS of these two equations are same, that's why LHS are same. F dash of x is equals to phi dash of x. A is less than or equal to x is less than or equal to b. Okay. Now therefore take integration on both sides. We will get f of x is equals to phi of x plus c. Sorry, this is not by integration, this is by a previous theorem. That theorem is, if f dash of x is equals to g dash of x, then f minus g means then f of x is equals to g of x plus c. This is by this theorem. Okay, or here we can give reason, this is by theorem. Okay, so we will get capital F of x is equals to phi of x plus c. Okay, for some c belongs to R. Here put x is equals to b. What we will get? Phi of b plus c. Put x is equals to a. This is equals to phi of a plus c. Therefore, phi of b minus, f of b minus f of a is nothing but phi of b minus phi of a. Okay. is okay. Again, capital F of x is nothing but integration from a to x f of t dt. Okay, so we will get f of a is nothing but integration from a to a. See here, f of x is, here upper integral is x, so here f of a is integration from a to a f of t dt, which is equals to, obviously this function is any type of function, but if you take integration and simplify it, here upper limit and lower limit are same, that's why we will get f of a is equals to 0. Okay. Next is f of b, which is integration from a to b f of t dt. Okay, suppose this is equation 1. Now put these values in equation 1. Therefore equation 1 becomes integration from a to b. Here f of a is 0. F of b is integration from f of t dt minus 0 is equals to phi of b minus phi of a. That means this is equals to phi of b minus phi of a. F of a is 0, so no need to write it. So we will get integration from a to b f of t dt is equals to phi of b minus phi of a. So here we can replace t by x, f of x dx is equals to phi of b minus phi of a. Okay, hence we have proved which we want to prove. Okay. Okay students, we will stop here. In next video we will see first and second mean value theorem of calculus. Okay, we will stop here. Thank you.